Good afternoon, Physics 135 students, and welcome back for our next virtual class. I just wanted to follow up briefly and say that fortunately I was able to get healthy just in time for my conference, although somehow, unfortunately, I seem to have picked up shortly after getting back, and unfortunately, I've been sick most of this week. I hope that you all have been enjoying your spring break and are ready to get back to learning. I'll just mention that I learned a lot of really fascinating things about James Webb Space Telescope's discoveries for the first billion years, started a new research project, and met quite a few individuals that I read their papers but not met in person. So it was a really enjoyable time. If you'd like to learn a little bit more about the conference I attended, please feel free to reach out to me or attend my office hours. I might try to work in some of the material during we kind of have like the last session or two as kind of bonus topics, if you will. So I might try to work that in then. Anyway, on to today, we have a new icebreaker question. And for today's icebreaker, it's a little bit more on the silly side per se. Would you have to speak like a sailor every day or never say another swear word for the rest of your life? And I don't really swear that much to begin with. I don't really like speaking like a sailor, so to speak. Darn it. So in other words, I would definitely choose the never say another swear word, partly because it's something that I prefer to begin with. But just kind of a fun one. You can prefer either one, and you don't have to answer like, mm, like within your own persona, you can just invent a persona or say like, oh, you'd want to speak like a sailor because you're planning on robbing a whole bunch of booty uh, during whatever during your expedition to Treasure Island. All right, so please email me your answer, and then yeah, it'd still be nice if you all use the Discord, but it's really up to you all at this point. I have not been on there in quite a little while. Okay, and then you all had your annotated bibliography due March 1st. I've graded them all now. I think I did that during my conference, actually. And just a reminder that the half paper is due Sunday, March 29th. Regarding the annotated bibliography, there were some students that got really low scores regarding the number of references. If you're not doing a literature review, you don't necessarily need the 20 references mentioned in the rubric. But if you are doing a literature review, you definitely do, unless you show to me that your target journal would not require that many or more. So just a reminder that if you got a low score, you can always resubmit with the late penalty, and that would allow you to recoup most of your points. And in any case, the half paper and etc. are worth quite a bit more. So please, please, please work on these and feel free to reach out if you have any questions about instructions. Ideally, before things are due, but afterwards is also fine too. All right, so today we're going to really get into one of my favorite topics, admittedly, is related to the state of fusion experiments and the energy crisis. We'll be situating ourselves and bringing up, making sure that we're all on the same page first. So in terms of this kind of module on nuclear physics, we'll start with definitions of the nucleon, neutron, and proton. We discussed these a little bit last time or two times ago, but we'll want to make sure that all that is very well understood since they play really an intimate role in the processes of nuclear physics, namely fission and fusion. And so we'll talk about those in general first, and then really about solar fusion and the buildup of the elements in the periodic table. By and large, we won't really go into, an upper level astro class might talk about S process and R process, but it goes a little bit beyond the scope of the first 3 minutes. And then we'll talk again, kind of my favorite part really is about the energy crisis and fusion experiments. I have one worksheet for you all to work on today. And then next time, I'm going to try to make the lecture be somewhat on the shorter side because we have a lot of worksheets that I think are really useful. I mean, you all can let me know if you prefer more lecture to worksheets. I won't necessarily, change my stance on this, but you're definitely always welcome to give me that feedback. And I do take it into consideration more largely for future semesters than for this semester. Okay, so moving on, regarding nuclear physics. So we'll see that I did play around with the AI. Kind of, some of you said that having AI generated slides in terms of like the styling was kind of nice. So we'll see some of that. Ultimately, I didn't really like what the AI generated, so I tweaked really a lot of the content. And in some cases, I just stuck to like the main theme if I was really writing things from scratch. So for this part, for nuclear physics, our goals for learning, really for today, these are the 7 goals for learning that we'll have throughout this lecture. First, what is the difference between a nucleon and a neutron? Second, if opposites attract and like charges repel, then why is it that positively charged nuclei, which are stuffed full of protons, can actually be stable? Attention check 3. What general principle is really responsible for the release of energy from fission and fusion? Attention check 4. How is it that the sun in particular fuses elements together? Attention check 5. How are the rest of the elements of the periodic table formed? And attention check 6. What is the energy crisis? Just kind of a definitional item, which admittedly for this one, don't really have a lot of text per se. It's really more of encoded in a video, which I think is still like a good introduction to the topic, and I'll mention some things verbally. And then attention check 7, what are the different types of fusion experiments being performed today? And there's really 2 in particular that I'll focus on, with the third kind of up and comer in there. Although admittedly there will be many, many more than we'll be really chatting about. So if you have your own favorite fusion experiment that I don't mention, please do email me or reach out. I love to hear about everything that's going on. I should mention that I did my PhD in astronomy and astrophysics, but I almost did my PhD in plasma physics. It was really like a coin toss decision there. Not fully a coin toss, but I was down to Michigan for astronomy and astrophysics versus UC Irvine for plasma physics and beautiful weather. And astronomy won out. Okay, so first, regarding understanding the constituents of nuclear physics, we'll be talking about the building blocks. And in terms of the building blocks of an atomic nucleus, this is, again, like an AI generated atom. It's just like a schematic. The idea is that for every atom that really plays a fundamental role, this was borrowed from the AI, but it didn't credit Neil deGrasse Tyson. So that's another reason why you always have to be careful with AI generated content to avoid plagiarism. And so Neil deGrasse Tyson likes to point out that regarding the atoms that were forged in the fires of stars, really everything from the hydrogen in the water to the iron in our blood is made of atoms. And admittedly, hydrogen is not, I should say, forged in the fire of stars, but the oxygen in water is. And again, the iron in our hemoglobin is. Now, in terms of these atoms, so we have the electrons schematically as these blue kind of fluorescing or kind of neon colors, and then in the center we have these red and black things, and those are the nucleons. And protons are a nucleon that carries a positive electric charge. Now, the number of protons is really what plays the role in how that element interacts chemically, because for neutrality, you end up with the same number of electrons as the protons. So the proton determines the element, whereas for the neutrons, because they have a neutral charge, they don't actually change the chemistry, not at all significantly, but they do affect the nuclear state. In particular, they play a key role in the stability of the atomic nucleus, and they are the reason why the protons are able to be so close to each other. These neutrons act like glue, and so just a key point here is that a neutron is a type of nucleon that carries no electric charge, whereas a nucleon is a proton or a neutron. So it's kind of like a square versus a quadrilateral sort of definitional difference. Now, again, regarding why protons stick together and about really the key role that neutrons play, the idea is the strong force. So there's a gravitational force, which is always attractive. There is the electric force, where like charges repel and opposite charges attract. The strong force is what's responsible for the protons, which otherwise would electrostatically repel, nevertheless staying together in the nucleus. And so it's really these neutrons that are, they're not just neutralizing like the electrostatic repulsion, but they're overcoming the electrostatic repulsion because the strong nuclear force is, well, quite strong, at least within the bounds of the atomic nucleus. It drops off 1 over to r to the fourth power. So, in other words, much faster than gravity or electromagnetism, or really like the Coulomb law, I should say. All right. So technically, the strong force applies not just between protons and neutrons, but it also applies between neutrons, and technically protons and protons. There is no stable atomic nucleus which consists only of protons, and actually a neutron on its own will also decay. So really, protons and neutrons, they're like peanut butter and jelly. They just go together. You can't have one without the other, right? Some of you will disagree with me there, and that is acceptable on the PB&J side. But as far as atomic nuclei go, again, always protons and neutrons together. All right, so back to more of a AI generated slide. I do kind of like the little like widgets or symbols that they use here. So as we've learned before during our unit on special relativity, there's a relationship between mass and energy. And just a reminder that this is relating the energy to the rest mass, which is admittedly the part that we're going to really care about for fission and fusion. But just a reminder that technically, there's a quadratic at play, and there you could include the momentum as part of the energy as well. Now, regarding the role of neutrons, I mentioned that neutrons don't play a role in the chemistry and therefore in our definition of the type of element, but neutrons do affect, again, the stability. So, in addition to having hydrogen, which is canonically a single proton, we can have deuterium, which is one proton plus one neutron. We can also have tritium, which is one proton plus two neutrons. You might wonder, okay, well, in that case, can we have one proton plus three neutrons? And you could for a very brief period of time, but that neutron will decay into a proton, and then you'd end up with helium. So again, there are certain bounds of stability. Now, regarding stability and relatedly radioactivity, typically we say that something is radioactive when it can when that atomic nucleus can spontaneously fission, or in other words, break apart. And this primarily happens when there is a really large nucleus that basically has like too many neutrons per se, that one of them wants to become a proton, and then when that happens, the electrostatic repulsion can be stronger than the strong nuclear force that would be attracting. And then the like kind of two regions split apart, and you end up with two, well, different elements that have broken apart usually. And this can, regarding the like stability of a nucleus, there is a relation between, on the lighter side, the atomic number and the number of neutrons, we find typically an equal-ish number of protons and neutrons up to a certain extent, and then we need more and more neutrons to keep things stable. So we'll notice that to some extent, but you'd learn a lot more about it in stars and galaxies. Well, to some extent, definitely in stars and galaxies too, or upper level astro classes. And so now moving on to fission and fusion, I thought that I had fixed all these things. Again, I think that the AI is kind of nice, but I don't really love all of its styling. Okay, much better. So regarding fission and fusion, again, fission is primarily where you have kind of big atoms filled with many, many protons and neutrons. Examples would be uranium and plutonium, but you can also have potassium-40, um, in other words, like K40. And these can split into smaller atoms, and when this happens, a significant amount of energy is usually released. Now, for potassium 40, uh, there is, I guess, still some energy released, but it's a little bit on the light side. And regarding nuclear fission, there are big, big issues with nuclear fission because of the amount of radioactive waste, which is very difficult to clean up or to handle. Nuclear fission is also what was used in the early atomic bombs or atomic weapons. Nuclear fusion was used in the hydrogen bomb and the more sophisticated and more recent nuclear weapons. And really, it's the opposite. Instead of splitting things apart, which releases some energy, fusing things together ends up producing much, much more energy, and it's really related to the fact that in fission, usually you don't really have that much of a change in the rest mass energy. You're just reducing the binding energy, so there's some release of energy. Nuclear fusion, you typically have a neutron, which is slightly heavier, change into a proton, uh, or just you have the binding energy really a significant difference than the two particles were individually. And so this releases a lot more energy, but you need really high temperatures and densities in order for this to actually occur. So it's very difficult. And so for most nuclear fusion weapons, they also include a fission component to ignite the fusion part. Now, in terms of kind of the split between fission and fusion, iron 56, happens to be kind of the boundary, and that's because of the binding energy of the nucleus. So this is this key, like general principle for how fusion and fission release energy. The idea is that when you fuse elements lighter than iron, the corresponding sum, so if we take two hydrogen isotopes and fuse them into helium, the binding energy of helium is lower. So in other words, there is some excess energy which gets released during the process. And similarly, when you fission elements that are heavier than iron, like again, uranium, which maybe decays into thorium and something later, then again, there is a reduction in the binding energy, and that means that there's a release of energy. Whereas if we try to fuse elements past iron, the binding energy is actually higher. That is an endothermic reaction. It would require the input of energy. And same thing for fissioning elements lighter than iron 56 canonically. All right, so in other words, producing elements beyond iron when we're talking about fusion, or in other words, building up the periodic table, this is not an energetically favorable process. It can happen when there is just a tremendously excessive amount of energy, such as what happens during the death of stars. Now, in terms of understanding the buildup of the elements, let's get into solar fusion. So the way that this works is that at low energies, if we just have protons, again, they're both positively charged, they will electrostatically repel each other or electromagnetically repel each other. Whereas if they get close enough, in other words, if they have a high enough energy that they can get really, really close to each other, then the strong nuclear force can overcome that electrostatic repulsion and they can stick together. And admittedly, for just two individual protons, this never happens. We need really some neutrons to really help us out. And then the other thing is that technically, like classically, this would still not work at the rates that are needed in the sun. There is some quantum physics at play where basically they occasionally these um, nuclei will tunnel through the potential energy barrier, and that allows them to get closer than you'd otherwise expect. All right, so again, you need really high energies. And in other words, for particles to have on average a high energy, that means that they have a high temperature. And that means that really it's most favorable for fusion to happen in the cores of stars where the densities and temperatures are highest. So for our own sun, the process that at least schematically happens is you can have two protons fused together to form a deuterium nucleus. And I guess I was overstepping a little bit. So this does happen, but the rest of the process is much more favorable and much quicker, which is why for all fusion experiments on Earth, they really like start with deuterium and tritium. Now regarding step two, when we have one proton plus one neutron, this is called deuterium, or in other words, there's two, two nucleons. And then these collide with another proton, and then they end up forming what's called a tritium atom. And admittedly, there's the release of a positron as well as a neutrino, or the release of a gamma ray. Here we'll kind of gloss over some of those byproducts. And then once we have two tritium nuclei, we need those to fuse together, and you end up with something that would have six particles. It would have four protons stuck together, but that's really too many protons. So two of them get ejected, and then we end up with four things left over, two protons and two neutrons. In other words, this is nice and stable helium-4. Excuse me, I misspoke. This one is not tritium. When we take deuterium and add a proton, we get helium-3. Helium is anything with two protons. So pardon in being incorrect there. So again, for stars like our sun, we start with four protons. We add another two protons. So in other words, we kind of start with six protons, and then we end up with two protons that are free floating plus a helium nucleus, helium-4 nucleus. All right. And in terms of these byproducts now, so we have some gamma rays, we have positrons, excuse me, the red ones are positrons, we have neutrinos. These are all for conservation, not just of energy, but also conservation of electric charge, because otherwise, if we have four protons in and then two protons out, then we would be violating the conservation, not of energy necessarily, but conservation of electric charge, which is why we need these positrons. And then again, for the neutrinos, there's actually another thing called conservation of lepton number. If we have two antiparticles that exist here, then we need really two antiparticles that are so-called leptons. In other words, they're not nucleons. Then we need neutrinos. We could get by with electrons, but then we still wouldn't be balancing electric charge. So instead, we have neutrons to balance, or excuse me, neutrinos to balance the lepton number. So those are details. You don't really have to worry about that right now, although some of this information will come in handy for next week's worksheet. All right, and then the key thing here is that taking these four protons and considering everything that has come out, the total mass is 0.7% lower. And the gamma rays, well, the positrons and neutrinos contribute almost nothing. So it's really the gamma rays that are carrying a lot of this energy, a lot of this mass energy. And for stars that are a bit more massive than our sun, that are still in the main sequence, they do a bit of a different process. They could do that proton-proton chain, but it's less efficient than this CNO cycle. So you do need to have some previous generations of stars that have built up carbon, nitrogen, and oxygen. But once you do, you have um, basically carbon, nitrogen, and oxygen acting as a catalyst. So you still have one proton, two proton, three proton, four proton going in, and you still have a helium nucleus going out. And in terms of this process, the rates are a little bit different. So although it looks like a cycle, you actually end up depleting carbon and oxygen with time, and you end up with more and more nitrogen 14 with time, but just in terms of the kind of rates being different in this total process. All right, and in order for this to happen, I should mention that you need higher core temperatures, which is why this doesn't happen in our own sun, but it does happen in more massive stars. Now, in terms of this CNO cycle, in other words, we're really just converting hydrogen into helium, but there is a bit of a difference between the amount of C, N, and O that are cosmically available or abundant as a result of this process. And then for helium fusion, this happens not on the main sequence lifetime of stars, which is a concept admittedly you learn more of in stars and galaxies. But for helium fusion, well, you're simply fusing helium together. But this is really also called the triple alpha process because you really need three helium nuclei basically to bang into each other almost simultaneously to form 12 carbon. 8 beryllium is unstable. So, uh, in other words, the rate has to be really, really high. Like this helium nucleus needs to collide with that 8 beryllium in a very, very short time frame where this is technically true, but it'd be a little bit more faithful, actually, I would say, to just say that three of the helium nuclei are coming together. And just kind of if you imagine that, there's a random process, it's possible for two things to bump into each other. It's a bit more unlikely for three things to hit each other all at the same time. And that's why you need really high core temperatures, or in other words, really high energies for helium fusion to happen. And in terms of the fusion experiments, no one really cares about helium fusion writ large, although some people are working on it, because hydrogen fusion releases more energy. And helium fusion is, again, you need much higher temperatures. And then after we get to carbon, there are a variety of different atomic nuclei that are built up simply by adding additional helium nuclei. So helium nucleus plus 12 carbon, we end up with 16 oxygen, nice and stable, 8 protons, 8 neutrons. This 12 carbon is 6 protons and 6 neutrons. If we take another helium nucleus, we get to 20 neon. We take another helium nucleus, we can get to 24 magnesium. And again, part of the benefit here is that because helium has 2 protons and 2 neutrons, we keep this balance between the protons and neutrons. These atomic nuclei are very, very stable, at least up until magnesium. And then after that, things get a little bit more difficult. So we've built up, up to atomic number of 12. We still have a lot of the periodic table to go. Now, we do get up to silicon, but notice that we're not just adding a helium nucleus anymore. You could, but for more massive stars, they start to run out of the hydrogen and helium in their core. They've built up a bunch of carbon and oxygen, and it's just more favorable, as it turns out, that you have fusion of carbon and oxygen to form silicon, and then fusion of oxygen and oxygen to form sulfur, and then eventually you have enough silicon to fuse together to form iron. And notice that we're at 56 for the atomic number, but we're no longer balanced in terms of protons and neutrons. Sulfur also is not quite balanced. So this is again, where we've kind of crossed that boundary of kind of linear stability, you need to pack more and more neutrons in, and that's ultimately why beyond iron, fission becomes more and more favorable. Okay, so we're able to build up to iron uh, in the not main sequence stars, but in these massive stars that are getting ready to explode, basically. And the reason why iron, again, is this dead end, this is looking at the mass per nuclear particle. In other words, you can think of this as being related to the binding energy. So because iron, it has like really this minimum energy or minimum mass per particle, you again, if you fuse particles, then you end up with a release of energy because the bound like fusion product has a lower mass than the two initial constituents. And then same thing for fission. The result of fission is lower mass than the initial or the yeah, than the initial beginning element, and therefore you produce energy. So iron is at this minimum. That's why it's this dead end for fusion. And so it's totally fine to have fission, but the question is, okay, how did we build up elements beyond iron then? And in terms of how we did that, we think that you need a huge reservoir of energy, which happens in a supernova explosion. And the idea is that for these stars, there could be, as they collapse, they maybe had a huge iron nucleus. Those iron nuclei will start to split apart as the energy basically gets way too high for them, kind of like how we can have molecules at certain temperatures and then they dissociate. So eventually you just end up with protons and electrons, which get squeezed so close together that they end up forming neutrons and neutrinos. And these neutrons, again, typically they would decay with a half-life of like 7 minutes. They don't stick around for very long. But under these intense conditions, there are actually a whole bunch of other neutrons, and they end up being bound together into basically a giant atomic nucleus called a neutron star. And in terms of what these supernova look like, this is an example from the Crab Nebula. This was documented by ancient Chinese astronomers. Puzzlingly, it was not observed in Europe, although it might have been cloudy, is kind of what people think. So this is the so-called Crab Nebula. It's been, well, expanding for, about 1,000 years now. But all of what you see here is the result of that supernova explosion driving the material out in these really fantastic patterns. Supernova 1987A is the closest supernova that we've been able to directly see, is in one of the nearest by galaxies to our own Milky Way, where we really couldn't see the star, we could barely see it, and then it became really as bright as all the other stars in this galaxy, essentially. So for this supernova 1987A, kind of like the Crab Nebula, it produced a whole bunch of light kind of fluorescing on the gas surrounding it. And there is a whole bunch of material that is being built up and is actually kind of debated right now because, it's only been like 40 years, whether the material that's built up in this supernova, in terms of like dust grains, which could be even like prebiotic materials potentially, whether those stick around or whether they end up getting destroyed during the reverse shock. Okay. So again, even though it's energetically unfavorable to produce elements beyond iron, there's so much energy in supernova that, we're able to do it. It just ends up cooling the supernova remnant because it's an endothermic reaction to fuse above iron. And that allows us to build up to, in some ways, all the heavier elements. I'm glossing over S process versus R process right now, but we can definitely get gold, we can get up to uranium, we get a lot of elements. Now, some of these are only human made, as far as we're aware, like lawrencium and berkelium, etc., or americium. I think plutonium is the last naturally occurring element. Everything heavier is man-made. Um, but regarding the abundances of gold and uranium that we think a garden variety supernova can produce, it doesn't seem like the yield is high enough. And so this was a big puzzle for a long time, but thankfully we have some clues in terms of what you'd learn in Stars and Galaxies. Basically, half of the stars that we see in the galaxy are binaries, or in other words, they have close companions, like in Star Wars for the Tatooine system. Now, for binary stars, it's possible that both of them could actually become neutron stars. And if they're close enough and you wait long enough, then they could spiral closer in until kaboom, you have an explosion. And this is what we would call a kilonova then. In other words, it's not a supernova, but it's a big supernova, would be another way to put it. And the way that we know that these things exist is because before you have the impact, and the reason why they inspiral, you have the release of gravitational waves. And then afterwards, you end up with those two stars having merged. You presumably end up with a black hole that gets left behind. And then you still have the fragments of these stars and really like the merger product, if you will, of these two stars that's not a black hole being kind of spewed around and producing a whole lot of elements because, again, this is even higher energy than a typical supernova. And we've actually detected some of these events now. One of the first gravitational wave events, we've mentioned this before, this was detected by uh, I think that I have a typo here. I don't think Cagra was online then. I'm pretty sure this was LIGO and Virgo. And so this was a binary neutron star merger detected by the US and Europe. And as a result of this, oops, I guess I'll have to propagate that through slide by slide. But as a result of this, we have learned quite a few things. One is that gravitational waves are like photons, they travel at the speed of light. Two, we've learned that these otherwise enigmatic processes called gamma ray bursts are related to these kilonova and are marked by the emission of gravitational waves. Third, we've learned that these neutron star mergers happen at such a rate that they can contribute really substantially to the production of heavy elements. And I think that I am done with my fixes there. Yep. So as I mentioned earlier, when we have this merger, we think that the core probably becomes a black hole because usually these neutron stars are massive enough that their merger should exceed what's called the Chandrasekhar limit for, well, a neutron star. And then as a result, we end up with, again, the kind of spewed fragments of the original two stars out in space and forming heavy elements. We think that a single one of these kilonova can form 16,000 times the mass of the Earth of heavy elements. And this happens way more effectively than for regular stars. And therefore, we end up with a lot of the heavier elements, like 10 Earth masses worth of gold and platinum. Although this would not be so easy to recover in terms of the kilonova conditions and just the vast distances that this material gets ejected to. All right, and so now I'd like you all to pause and go over to Brightspace and work on the element creation worksheet. You should have enough background material to work on that worksheet by now, which is admittedly, no, I'm thinking of the uh, light matter and antimatter when I think. But anyway, so you should be good to work on that worksheet now. Okay, and then hopefully you paused the video and worked on that. Next, we're really into the last part of this class. We'll be talking about the energy crisis. So I try to avoid anything politics related. The energy crisis has been an issue for decades now. If you look at the growth of energy consumption compared to the the energy available, it seems like if we want to keep on leveling up our society, we're going to need better systems than what we have in place right now, especially if we want to really become a galactic civilization or a spacefaring civilization. Now, nevertheless, this is kind of related to oil and greenhouse oil and gas, we'll say. And let's go ahead and take a look at the video.
Early this week, after the outbreak of war in the Middle East, the EU experienced its most serious shock to energy markets since Russia's invasion of Ukraine. Oil and gas prices.
And I will mention that I was a postdoc when I arrived very shortly before, unfortunately, Russia invaded Ukraine, and it was very cold there because there were huge energy issues, and you basically could not use clothes dryers, which is kind of interesting if you can imagine it. Um, you could use a wash, and then you just had to hang dry your clothes, even in the winter when it was freaking cold.
Surged after the Strait of Hormuz, through which roughly 20% of global oil supplies and a similar share of the world's liquefied natural gas, or LNG, trade passes, was effectively blocked. At the same time, Qatar, the world's third largest LNG exporter after the US and Australia, announced that LNG production would be halted at its main facility, one of the world's most important export sites. This is terrible news for the EU, which has become reliant on Qatari LNG and has spent the last few years grappling with high energy prices after it committed to weaning itself off cheap Russian gas.
All right. And so part of you can keep on going through that video. It becomes much more politics related, which is not really the point of me introducing the video. The main part was really that last part that was being shown there with respect to the energy prices. So Europe has really dedicated themselves to switching to renewable or well, uh, energy sources that don't require combustion is maybe one way we could put it. And the issue there is that still a lot of the energy that they rely on is related to combustion. And partly that's just because solar and wind do not produce enough energy in like really convertible or storable properties. So France is doing okay because France has a lot of nuclear fission plants. But if you're in a place like in some places in the US or Japan where there can be earthquakes or tsunamis, then that's not super ideal. Or even for like Three Mile Island in New York or Chernivtsi in Russia, there have been meltdowns for reactors. So fission is not really ideal. So really, nuclear fusion, I would argue, is the solution to the energy crisis. And for sure, if we want to become a more technologically advanced civilization, fusion is going to be the way to go. So, in terms of the benefits of fusion, one thing is that whereas for uranium and plutonium, keep in mind that we need those kilonova to produce those. In other words, it's not like there's an infinite amount of uranium and plutonium, but there is a pretty good amount. Um, for but they need to be mined, etc. For fusion, we really just need hydrogen. And for tritium, actually, it's a kind of really big problem. But for deuterium, we can get this from seawater. So that part is really okay. Tritium's a lot easier to fuse than deuterium, but if we can get deuterium reactors, then we're good. Now, in contrast to fission having a lot of safety concerns as well as the radioactivity, fusion is much better because it doesn't produce, again, like greenhouse gas emissions, and fusion doesn't produce radioactive waste. And for fusion reactors, if there's an issue, it's a really tenuous gas that you're working with. And so what would happen is sometimes you'd like melt the reactor walls and then you end up with some hydrogen gas like deuterium leaking out. Big deal, big whoop, not really an issue. And so in other words, it's not possible to have a runaway reaction because if you have an issue, you just don't have like enough energy. It's really hard to do fusion. So you basically just get fusion in a stable process, if you run into an issue, you basically just stop fusing. So, and then the other benefit is that, again, for fission, you produce some energy, but fusion, you produce way more energy. So, in terms of, again, becoming like a spacefaring or really galactic civilization, it's not really feasible to use combustion to get to the stars. You need way too much fuel. For fission, it's a little bit more feasible, but again, you end up with so much more energy for fusion than fission. So, it's really the best way to go. Now, in terms of experiments, there are really two main methods that are currently being explored. There's magnetic confinement, which includes most typically or prototypically tokamaks, although when I was in Germany, they had just built the largest stellarator ever constructed. I don't know who holds the world record now. I think Princeton had maybe one-upped them recently. And as far as the tokamaks go, they're basically what you see typically when you Google fusion experiments. This is related to projects like the International Thermonuclear Experimental Reactor, or ITER, in Nice, France. And the idea is to use really big magnets that really squeeze the plasma into a donut shape and accelerate them to really high speeds. Again, the issue is that if this really high energy, in other words, hot plasma touches the walls of the container, then you end up melting the container walls. So it's really important to have your magnets really figured out to avoid breaking or busting your experiment. And then on the other side, instead of magnetic confinement, so the confinement here is about having really high densities as well as really high temperatures. Instead of magnetic confinement, you can also have so-called inertial confinement. So inertia is about really like the speed or energy, and this is typically done by shining lasers on these really small pellets, where the idea is that if you shine these ultra powerful lasers in kind of a head-on collision, then if you imagine like pushing on a cup of water, I can slide it across my desk. If I push on each side, then I end up squeezing it. If you're super strong and you have a really weak glass, then maybe you break it. And sort of the same thing happens if you squeeze on that pellet with really high energy, then that can compress it enough until it does fusion. So it's almost like for bombs, but instead of using a fission bomb to ignite the fusion bomb, the idea is to use these lasers in a much more controlled way, where ideally you can also extract the energy, not just irrevocably release it in a bomb, but release it in a way where you can use that for other purposes. So there were some recent breakthroughs for NIF, not really for ITER, but certainly there have been improvements in magnetic confinement over the last 5 to 10 years. And in terms of these breakthroughs, one of the ones that really received a lot of press about 5 years ago, maybe is not on your all radar now, but this was heralded as being one of the most impressive scientific feats of the 21st century. Admittedly, the people that said that were people in the Department of Energy that were funding the experiments, as well as Lawrence Livermore National Lab, excuse me, who were running the experiments. I do really love, I should say, the Department of Energy and the national labs, but I'm a little bit skeptical of this headline. In particular, there is kind of an issue. Excuse me, maybe this was 2022 instead of 2021. Now, their claim to fame is that they produced more energy than the lasers deposited. So they were finally past break even. The issue is that it required about 100 times more energy than what they produced just to turn the lasers on. So, admittedly, maybe that's not, the biggest deal if you can have you just turn on the lasers once, you have a one-time cost of 300 megajoules, and then you just do this 100 times, and then you're really actually or actually more than 100 times because you're only releasing 1.1 megajoule. But if you do it uh, 300 times, you're definitely in the positive. The issue is that although this produced lots of energy, it wasn't captured. And the problem really with these inertial confinement experiments is that you have these pellets. You have to like kind of drop a new pellet into place, and usually that involves turning the laser off and back on. So that's it. So there are huge, huge issues here still. It is definitely an improvement. I don't want to take that away, but I just felt like it was a little unfair in terms of the hype. Although it did r end up producing a lot of funding going towards different fusion experiments, which is maybe a bad thing for the investors because we're still nowhere close. But on the other hand, I do love the concept of getting fusion in the near future. So maybe it's a good thing. All right, and then for ITER, even bigger problems here. NIF, the National Ignition Facility, had, you know, some cause for celebration. ITER has not really had any cause for celebration. Um, Instead of the International Thermonuclear Experimental Reactor, it could also be styled, it is the eternally delayed reactor. ITER is probably one of the longest running scientific collaborations or experiments that has still not actually seen the on switch turned. Um, it was started in 1978, and believe it or not, this was a collaboration between the USA and the USSR, as well as Europe, which back then was styled the European Atomic Energy Commission, in Japan. All right, so it started in 1978, but then uh, basically it stalled when Gorbachev was kind of vying for power, etc. Made some small progress in 1985 or so, but really the technical objectives were not set into place until 1992, 24 years later, right? So a long time after it started, did they actually get some technical objectives put into place? And it's just despite a lot of physicists in the US and Russia and other places really pushing for this, but really big geopolitical issues perhaps is the issue. The reason why is meant to be this huge international collaboration is the idea is that this is way too expensive for any single country to build. So it's meant to be really like the be all end all of tokamak experiments. All right. And then after 1992, we had our objectives in place. It took 9 years before they finally had an acceptable design. It took quite a while before even the first design was, I think, like 6 years before the first design came into play. And then that design finally got reviewed in 2006 to 2007. And between 2001 and this review that ended in 2007, there were some additional members that were added, like China, South Korea, and India. On the one hand, that means more money, but on the other hand, that means bigger geopolitical and to some extent language related issues. Now, assembly finally started in 2020, and between 2007 and 2020, we had Kazakhstan and Canada join into ITER. And in 2022, the idea was that there would be a first plasma in 2025. Actually, when I started my PhD in 2015, I was promised that assembly would have been done and first plasma would have happened in 2021. So, there's a little bit of a revisionist history, I'm sure, at play even here in terms of estimates. So, 2022, first estimate for the plasma was 2025. Now, there are big issues in the manufacturing partly because different countries have different roles that they're playing, and there just has not been very good either oversight or communication between groups, or a bit of both. And now we're not expecting first plasma until 2035 to 2039. That's partly because of one, the issues in the manufacturing that were a really big issue. There were like cracks that were found in some of the materials. There was also an experimental or more theoretical study, I should say, that showed that the load that would be placed on the tokamak would actually be 5 times higher than they were expecting, which means that they might need even stronger materials to effectively confine the plasma because it would really suck if you built this extraordinarily expensive thing and then the plasma walls melt and then you have to rebuild it, right? Okay. So why is it that fusion is just so hard to get done on Earth when we have it on the sun? There are a couple of issues. I mean, one thing is that in order to have fusion really happen sustainably on the Earth, we need way higher temperatures, and that's because we don't have the densities of the sun as a result of the sun having, enormous amount of mass, which means a ton of gravitational squeezing. So we don't have that at play. So we need much higher temperatures, 150 million Kelvin, which is really extraordinarily hot. And that's part of the reason why some people are actually interested in looking at not hydrogen fusion, but some heavier elements, because in order to do any fusion, you need really high energies. And then, uh, in addition to this being an issue, um, there's really like a lot of disagreement about how to do fusion, right? So there's the tokamaks for magnetic confinement. I've just mentioned verbally that there are stellarators, which are another magnetic confinement. They're like the tokamaks, but instead of being regular donuts, they have these kind of swirly patterns. They're kind of cool looking. And then aside from magnetic confinement and inertial confinement, this technically falls under inertial confinement, I should say. But there's a different type where instead of shining lasers, the idea is that you use a magnetic effect called the Z pinch. And so Sandia National Labs has been exploring so-called pulse power fusion since the 1960s. The Z pinch machine is not nearly that old. It's been around since the 90s, I want to say. This began really as an offshoot of nuclear weapons research, and really for the Sandia Z-pinch machine, it's pretty impressive. It requires 23 million amps of electricity, and it ends up generating 350 terawatts of X-rays, or in other words, 2.7 megajoules. And now let's go ahead and actually take a look at so this is actually a video. Let's see if I can get to full screen. This is a you know definitely a concept video produced by Pacific Fusion, and so this is a different commercial company. Sandia National Labs is part of is funded by the Department of Energy or the federal government. This is by a startup that actually uses the same code that I use for astrophysics. They do it to run their fusion kind of simulations in preparation for their physical experiments. And so this is a kind of a zoom through of like how you might have a pulse power plant looking like. All right, so you have all these like batteries basically that are responsible for producing that huge amount of ampage or electricity. And so those are kind of like all in an array. And then when they turn on, then zoom, you end up with a whole lot of electricity, and that really high voltage means that you can have a really strong magnetic effect at play, and then ultimately you end up pinching that thing in the very center to perform fusion. And then voila, we have a fusion plant. So that'd be very cool. It's there's a lot of people that are very interested in this. Pacific Fusion is again like one of the names. So I very much hoping that this becomes a reality. I think I would say that my two dreams of being able to see in my life, which at some point I would really like to contribute to, but would be going to Mars or going to some body beyond the moon as well as fusion. They're both, I would say, equally lofty at this point ambitions, but both would be rather vital in terms of technologically advancing our civilization. Okay, so that's the end of today's lecture. We're pretty much right at 1 hour, which is great, especially in case you needed to pause the video and take breaks and rewind, etc. So just in case you didn't do that attention check uh, 8 for the element creation worksheet, please make sure you do so. I guess the benefit of if you didn't do it back then is in terms of the amount of time you have a sense for how long you should spend on it. I'm expecting it to be more of like a half hour-ish worksheet. But if it's more of like an hour or so, that'd be still reasonable. If you run into any issues or challenges, please do email me. Happy to chat with you over office hours or over email. All right, take care. Bye bye.